Yeah. Yes, I'm very happy to be virtually here today with you. My name is Fernanda Duarte. I'm professor of computational chemistry at the University of Oxford. I have been here for 2 years. Times fly. I'm originally from Chile, and I have been working, did my PhD there, then working as a postdoctoral researcher in Sweden, then the UK, and finally have arrived here when I started my own group here at the Department of Chemistry.
So, what brought you into the field of computational chemistry?
Actually, during my undergrad, I was doing experimental chemistry, more specifically ruthenium complexes, and I was very interested on exploring ligands that will enhance or improve the emission or absorption of some of those compounds. I was really interested on trying to elucidate and make predictive models to do that more efficiently rather than being in the lab. And at the end, I decided that was a much more challenging project that required a PhD probably to work on. At the end, probably I didn't do any metal chemistry during my computational chemistry PhD, nor during my postdoc, but actually that was the specific chemistry problem that brought me to this area.
What aspects of computational chemistry or data chemistry did you find challenging at the time when you started in the field?
There were two types of aspects. Probably the first one was related to using different tools that you will be used to learning new languages. At that time, was required to start learning Fortran, and then even working with terminals. So that was a practical challenge that actually was very easy to solve once you get into the projects that you're working. But probably the first kind of steep learning curve that I had. And then the challenging aspect about the chemistry or the computational chemistry that I was looking at, there were so many methodologies, specifically working with density functional theory, for example. How do I choose my methodology? What is good? What is bad? And having kind of general principles to work with was and still remain many challenges.
Right. Yeah, I would agree. Do you believe that these challenges still remain within the field or have they kind of resolved out?
Challenges related to kind of how to choose probably density functional theory to work with remain very open. The good things are many things are coming to complement density functional theory, which still remain very powerful, but I think that the challenge of how to build properly a density functional theory that is general for all the chemical problem is difficult, and we have just now learned what are the weaknesses of the methods that we used to use. So I think that we have learned from going from using viscerally, which we realized that was good for many things, to learning why is good or why is bad. And hopefully we continue learning about those approaches and probably learning how to select them better rather than designing one per se. But many other methodologies are coming to complement that and trying to solve those issues from more advanced ab initio methods to machine learning approaches. So I think that they are trying to help to solve this issue of how to better model electronic structure for chemical properties.
In today's world, what are the challenges that requires addressing that would have the most impact?
I think that there are so many challenges related to environment and so many challenges related to kind of medicinal chemistry that we don't really value sometimes the impact that we can have as chemists. We can see, for example, this year with the current virus going on, all the chemistry work that has been going on for many years related to developing antibiotics, synthesizing molecules, or maybe with CO2 activation, so many catalysts that have been developed for those aspects. So I think that there are many big challenges for society that we can solve with our chemistry knowledge, and we can advance with computational chemistry. So I think that we are very powerful people in that sense that we can have a huge impact. Related to challenges more in the computational side is personally we think that is modeling chemical reactions in the condensed phase, where we still lack the methodology that is both accurate and efficient to give answer to more complex processes. taking place in solvents, but maybe combined solutions at the interface with the heterogeneous catalyst. So I think we have a lot to learn and improve in the methodologies that we use.
So there is skepticism in computational modeling for proposing mechanisms or making predictions. So as a computational chemist, do you as well approach computational modeling with caution?
Oh yeah, I think that everyone should, and any experimentalist collaborating with a computational chemist should be kind of make sure that they are the most skeptical people to deal with. And I think that as a computational chemist, if you were collaborating, for example, it's important to point out the weaknesses and the strengths of the methodologies that we use early on. I think that helped to build some trust in some collaborations that are very important, and also be aware of the questions that we're asking are the correct one for the methodology that we're using. What we try to do in those cases is make clear early on what is the question that we want to ask, and if the methodology that we have is able to provide an answer. Sometimes if we want to get small energy differences, maybe the methodology that we are using, it has an error that is much larger than that. So it's impossible to expect high accuracy in or kind of black and white predictions, binary prediction for such problems. So I think that be aware of the weaknesses, but also complement some methodologies. Maybe one of them per se is not the best one to address this problem, but can give you some information. And I think that using this set of different approaches in the same way that experimentalists will try to tackle the question from different angles is something that can help to overcome some of the challenges that we still have to reach the accuracy that we will expect.
Right. So then, how do you guide a skeptic chemist to trust in these tools?
I think that the first part is spend a bit of time initially in explaining those. And of course, people have to be willing to learn. An experimentalist that is just not willing to learn those aspects can be critic and just as a belief more than from knowledge. But I think if people is willing to learn, as any scientist should be, it's important for us to point out, as I mentioned before, challenges and the limitations that we have as a starting point. And if we mention those limitations, in our case, has happened with when we predict activation energies. They can be off by many kilocalorie moles.
Right.
But actually, if we combine information related to kinetic isotope effect, to linear energy relationship, NMR data, and all of them as a whole can give us a kind of a unifying framework to understand the chemistry, I think that will provide the kind of solid answer that will help to answer some question. So using one methodology is also quite limiting, but if we use all the methodologies, this toolbox that we have, and we know the limitations of each of them, present them, and we try to teach those aspects to experimentalists, I think that they will be willing to learn and to trust the results that we are providing.
So as we are progressing into a more AI or robotic system, it is probable that experimental scientists will need to acquire new tools to assist in the automation process. So what tools or advice would you recommend so that we can learn automation and or computational chemistry easier to someone that's outside the field?
Well, I think that this time is quite amazing that people is willing to share knowledge online. And in many cases, we will all go to Wikipedia or YouTube for a video. And I think that sharing and then some tutorials in GitHub. So actually asking people from the community to share those kind of tools is great. And for those trying to learn to explore those areas, but also in the case, for example, of machine learning, there are many online training courses that are great. They are not related to chemistry. Sometimes you will be looking at how to optimize buying a house or a car, but the methodology is there. More technical aspect, MATLAB or those tools, if you have access to, they are a very friendly way to get started before you get into other ones that are just kind of terminal interfaces and don't have any graphics.
So, how can we continue the message in amplifying the research and innovation of the Latinx and the Black scientific community?
That is very important to empower those communities, and it's not only saying providing a statement on that, which is very important, is the first step, but also being proactive in promoting people. So I think that anyone that now is thinking about inviting students to a conference or to an organizing committee should be considering, can I invite someone from those communities? I think if those communities start to be involved in committees and in activities that are kind of leading new projects, will be the way to amplify the kind of the message that those have, that is introduce equality and diversity, not only for the Latinx community to introduce more Latin American scientists, but also kind of diversity widely.
Right. Yeah, let's have everyone included. That's great. So the Supreme Court Justice Ruth Bader Ginsburg famously once said, women belong in all places where decisions are being made. It shouldn't be that women are the exception. So, you, as a top scientist within the academic field, what advice would you have for getting into the room where decisions are made and to remain competitive?
I think that I'm always, many people are around it very scared of speaking in some big committees and those meetings with very senior people. But I think that it's important to try to be yourself.
Mm-hmm.
There will be people that may be very aggressive, very confident in cases of conferences, but I think I will try to be yourself, be polite, willing to listen to others. And I think that many of the leading politicians during the crisis last year, have shown that many kind of women can have a very powerful role, not because they are kind of speaking very loudly, but actually because they can bring people together and communicate a message that resonates with many others. So I think that we have this power that I hope many men will also kind of promote, that is just trying to be yourself and trying to listen to others and communicate a message that is saying why we want to do something. It's not like just a statement, but give a vision of why it is important for someone else. In the case of diversity, for example, it's not just because I come from a minority group and I want to be into group, but actually because that is important to science, because we know that will make better science. So I think that people is willing to listen if there is a message that they feel involved, and I think that we can be very powerful without being aggressive or without being harsh to others.